Welcome to qnawire.
So in this video, we're going to work through question 116 from chapter 20, which says the heaviest member of the alkaline earth metals is radium, a naturally radioactive element discovered by Pierre and Marie Curie in 1898. Radium was initially isolated from the uranium ore pitchblende, in which it is present as approximately 1 gram per 7 metric tons of pitchblende. How many atoms of radium can be isolated from 1.75 times 10 to the 8th grams of pitchblende, given that 1 metric ton is equal to 1,000 kilograms? One of the early uses of radium was as an additive to paint so that watch dials coated with this paint could glow in the dark. The longest-lived isotope of radium has a half-life of 1.6 times 10 to the 3rd years. If an antique watch manufactured in 1925 contains 15 milligrams of radium, how many atoms of radium will remain in 2025? So let's start out with this first question. How many atoms of radium can be isolated from 1.75 times 10 to the 8th grams of pitchblende? So we start out with our 1.75 times 10 to the 8th grams of pitchblende, or I've written that here as PB, and then I know that there are 1,000 grams in 1 kilogram and 1,000 kilograms in 1 ton. So I'm converting this to tons of pitchblende. And then I know that for every 7 tons of pitchblende, I have 1 gram of radium. So now I'm in grams of radium at this point in the calculation. Then I can use my molar mass to convert grams to moles of radium. So I divide by the molar mass. And then I know that I have an Avogadro's number of atoms in 1 mole. So I have 6.022 times 10 to the 23rd atoms of radium per 1 mole of radium. So all of this evaluates to 6.78 times 10 to the 22nd atoms of radium. And then we want to answer our second question. So given the half-life of radium, if an antique watch manufactured in 1925 contains 15 milligrams, how many atoms of radium will remain in 2025? So when we're talking about nuclear half-life calculations, we can use this equation where A of t, the amount at some time t, is equal to A naught, which is the initial amount, times 1/2 raised to the power of t divided by t 1/2, where t is the period of time and t 1/2 is the half-life. So our period of time in this point is from 1925 to 2025. 2025 minus 1925, that's just 1,000 years. And our half-life is 1.6 times 10 to the 3rd years, or 1,600 years. Our initial amount, we were told we have 15 milligrams of radium. So we convert milligrams to grams, and then we divide by the molar mass to convert grams to moles. And then I know I have an Avogadro's number of atoms in each mole. So I multiply by Avogadro's number, and that evaluates to 4.07 times 10 to the 19 atoms. So that's how many atoms I'm starting with. That's my A naught. So let's plug in everything we know, A naught t and t 1/2. So our amount at time t is going to be 4.07 times 10 to the 19th atoms, that's our initial amount, times 1/2 raised to the power of 1,000 divided by 1,600. And this evaluates to 2.64 times 10 to the 19 atoms. So that's how many atoms we would have left in the year 2025.